Hi, my name is Amir, and I'm going to present the black box adversarial attacks to image classification networks via autoencoder and deep reinforcement learning. It is a joint work with Lyue and Professor Wen-Guey. So let's begin by defining what is an adversarial attack. Suppose we have a classifier C that has been trained on some dataset such as MNIST. On an input of a handwritten digit, the classifier would output a probability distribution vector over all possible classes. For this particular input, the probability of class 5 is the highest, so this image is classified as 5. Now we have an adversary, that the adversary would take the same image and he tried to perturb the image in such a way that when he sent this crafted adversarial image to the same classifier, he would mislead the classifier to classify it as another class. And in this example, this crafted adversarial image has been classified as 9. So the adversarial example may produce many different outputs. So the question is that which of these adversarial images is the best? Many papers, they try to define the n norms, and then they would say that they want to create an adversarial example so that the distance between the original image and the adversarial image is as low as possible. The other way is to discuss the imperceptibility, that human eyes can distinguish this one as 5, but the classifier maybe is fooled and classify this one as 9. So in the previous approaches, they try to perturb the pixels directly so that they take the original image and they add some white noise to create an adversarial example. However, this line of work, they can only achieve a very low imperceptibility and transferability. We will discuss these issues at the end of this talk. In our solution, we try to use autoencoder and reinforcement learning agent, and we want to perturb a feature space rather than the pixel space. So these are our contributions. We propose a targeted black box adversarial attack. We use autoencoder and a deep reinforcement learning to create these adversarial examples on the feature space, not on the pixel space. And then we show that by perturbating the feature space, we can achieve a very high imperceptibility and transmissibility rates. And we also show that the adversarial examples that we have obtained can mitigate those sanitization techniques such as magnet. So let's define what is adversarial example. We have two types of adversarial examples, targeted and non-targeted. For the targeted one, for every input tuple of image and its corresponding label, the, the adversarial example might want to manipulate this X to create its corresponding adversarial image Xi adversarial so that it can fool the classifier to misclassify it as some chosen class T. Versus for the non-targeted attack, the goal of the adversary is to manipulate this picture so that to fool the classifier and the classifier misclassify this image as anything but the actual class label. In doing so, the attacker has two ways. The first one is a white box access, where the access adversary has complete information about the classifier. It knows its structure and also its weights. The second type, which is a bit harder one, is a black box attack, where the adversary can only query the classifier. You have two existing work. The first one, assume that it has a white box access to the classifier, and you use a gradient-based idea to craft this adversarial images. But nevertheless, the white box attack is impractical in practice, and also they perturb the pixels directly. The second result, the gen attack, they use a gradient-free idea. The idea is to use a generic algorithms, and they create many generations to find the adversarial image. Some of the disadvantages of this work is that they would require a large number of the queries to the classifier in order to create one adversarial image. And they still work on perturbing the pixels. And at the end, they obtain a very low imperceptibility and transferability. So what is our approach? Let's see the overall picture. So on an input image, we send this input image to an autoencoder network to encode this image and reduce the dimension of the input. And then we get the S0. This is the features. We use these features as a state representation, and we send this one to a Q network. So our agent would now observe his state, and then he can take some actions. In the training phase, he would take some random actions with probability epsilon, or he would take an action that has the maximum Q value. And after he chose his action, he would take the action and directly perturbate the state. And then he create a new state. Then we would replace the current state with the crafted state. And then we will try to decode this image and we would obtain our first adversarial example. Now the agent can query the classifier to see whether the action that he has chosen is a good action or a bad action. So overall, we have two phases. In the first, we have training phase and a testing phase. In the training phase, we start with a random policy, and the agent would interact with the classifier so that he can refine his policy. In the testing phase, we obtain our optimal policy. So the agent would make much fewer queries to the classifier, and for every state, he would follow the trajectory that is suggested by the optimal policy. So as you could see, our goal is actually to learn a policy. So in order to learn an optimal policy, we allow our agent to interact with this target network F. And also we define a very good reward function that would tell the agent whether the chosen action was good or bad. And then in the training phase, the agent would follow some trial and error approach. And in this way, for every state and action pair that he visit, he would record his experience into the Q network. Then, if the agent is at a state ST, the action that contributes to the highest Q value would means that it is more likely that agent can create an adversarial image. So in our system design, we have the training phase and the testing phase. In the training phase, now we are going to introduce the state and action spaces and also discuss the reward function. And then later we would show how do we generate the adversarial images. So for the state representation, as we said, we get the image X, we send it to the autoencoder, and we get the encoding space as features to represent the state. So we use sigmoid activation for this encoding neurons. So the range of any of these features is between 0 and 1. For the action space, our goal is to perturb the feature space directly. So we define an alpha and we also many different actions that every action would add or subtract some small value alpha from that specific feature. Suppose that we are in a 2D space and we are currently at this state. And then we have defined 4 different actions, and every action you can see that it can add or subtract some small value from the feature. So if the agent take any of these actions, he might find himself in this corresponding states. The next and the most important thing is our reward function that would guide the agent to learn its optimal policy. So we have some goals for this. We want to successfully attack the target network. With that, we want to attain a very high probability for the target class. And then we also want to retain the original shape. With that, we mean that we want the adversarial image to still obtain a high probability for the original class. So this is our reward function. In the following slide, I will go to the details of any of these conditions, and then we will see how it works. So as we discussed, the range of our features is between 0 and 1. So if the agent take any action and take us beyond that space, then we will say that this action is invalid. And we would punish the agent with a very high penalty minus kappa. And if the agent is in some intermediate state, then we define the reward as following. We want to give a higher reward to action that would increase the probability of image to be in the targeted class. And then we also want this image to retain some high probability for the original class. So as you could see in these two examples, the agent is in this state, and by taking these two action, he would end up into two different states. So this reward function would give higher reward to this particular action because it gets us closer to the target class, versus the other action would get a very lower reward because is actually going to the opposite direction. We have two conditions that with that our algorithm would halt and output adversarial example. So the first condition is that, of course, the adversarial image can fool the classifier to misclassify it as class T. And the second one is that we want to define a boundary, and then we want this adversarial image to fall beyond this boundary. So for this particular example, adversarial example, or algorithm would halt, and this would be one of our adversarial samples. Once we have found such an adversarial sample, we also provide some bonus to those adversarial images that they keep their original probability of the original class pretty high. So the idea is that they would still preserve the same shape as the original class. So let's see how do we generate the images on the testing time. So we take the input to the autoencoder, we get the feature or encoding of this input image, and then we would we would use that feature as a state representation, and then the agent observe this state, and then instead of taking sometimes some random action, now we would just follow the action that maximize the Q value function. So the idea is that the agent would follow the trajectory that is suggested by the Q function. So now we would perturbate the state with the definition of that action, and then we will try to craft our first adversarial example. Now our agent would query the classifier C to see if it succeeds or not. So if it fails, then it means that there are more actions that the agent has to take. Otherwise, if it succeeds, then the algorithm would just halt and use that adversarial example as output. In order to evaluate our result, we have trained our model on the MNIST dataset. For training dataset, we have 60,000 images, and we have 10,000 images for the testing set. And these are the details of the number of the pictures on each class. In order to train our target network F, we have designed our target network F with these details. And then once we have trained this target network, we have achieved 99.16 accuracy in the testing set. So let's define the attack success rate. So for any given image on the test data set, we would send this image to our algorithm, and then we try to create the corresponding adversarial image that can fool the target network to misclassify it as target T. And if so, we count it as a successful attack. So we have compared our result with many different results out there. And the first one is the result that has a white box access to the target network. And you see that the attack success rate is 100%. The other ones, they assume that they have black box access to the target network. And you see that their attack success rate is far less than 100%. But as you could see, our approach obtained a reasonably good attack success rate. One of the interesting things is that you see that the L0 and L2 norm of the images, the distance between the image, original image and the adversarial image that created by our algorithm is significantly higher than the other one. So the other papers, one of their goal is actually to try to keep the distance between the original and the adversarial image as small as possible. So in doing so, they define some p-norms and try to minimize them. But Actually, these metrics are not really equal to the human perception. Allow me to show you this example. On the first column, you see some samples from the MNIST dataset, and the rest of the columns are adversarial images created by different algorithms. So in the second column, you see our approach, and these are the corresponding adversarial images that we have created with our agent. So one interesting thing is that the L infinity distance is significantly higher than the other ones. But what you can see is that the quality of the image that we have generated is much higher than the other ones. Also, please notice that since the other ones only work on the pixel space, so the same shape and the stroke will preserve on the adversarial example. But as you could see for our algorithm, because we are working on the feature space, you see that our agent has changed the strokes a little bit. So whether this result is better than the other one, it is subjective to the audience decision. The other issue is transferability. Suppose that we have trained our agent by querying the classifier A, and then on the test time, our agent has created some adversarial images. So now the question is that what happens if we send these adversarial examples to another classifier B and to see whether or not our attack would still be successful? So to answer that question, we have created two different classifier B and C. For the details of these classifiers, please read our paper. So after conducting our test, we see that for the targeted class, the gen attack would only retain 1.46% of attack success rate. And for the non-targeted attack, you see that it only obtained 6.21% of transferability. However, as you could see, after we send our result to two different classifiers, you see that for the non-targeted and the targeted classes, we still obtain a very high attack success rate. Then the next interesting question that we had was that what happens if they use sanitization techniques such as magnet? So the idea of some sanitization techniques such as magnet is that before you send the actual image to the classifier, you send this image to another network so that they can remove some of the noise and sanitize the image. So then we ask our question that what if those target classifiers are equipped with the magnet, then what happened to our result? So interestingly, you could see that even though the other results, they have obtained a pretty high attack success rate, but once we equip the target network with the magnet, you see that their attack success rate drops significantly. Versus in our result, you see that we have significantly higher attack success rate, even though the targeted network has adopted the magnet. One of the reasons is because we are working on a feature space rather than the pixel space. Another interesting thing to discuss is the number of the queries to the target network. So we observe that in the training phase, we have 400,000 queries to obtain our optimal policy, and that is just for the training phase. Once we are done with the training phase, on the testing phase, we realize that on average, we only need 22 queries to craft an adversarial example. So you compare these numbers with the other result, even though they obtain a little bit higher attack success rate, but they need to have a significantly higher queries to the target network in order to craft their adversarial images. So to conclude this work, we have constructed an adversarial example by perturbing the feature space and using a reinforcement learning agent. Once we have trained our agent, then crafting an adversarial example just needs a significantly fewer number of the queries comparing to the other works. And our adversarial example achieved 94% attack success rate and remain over 65% of that attack success rate if the targeted network is equipped with some sanitization techniques such as magnet. And we think that our approach is a promising direction for improving the transferability and imperceptibility for adversarial images. Thank you for your attention.